Now let's consider heating a mass of substance. When we add heat energy to the substance, delta U will increase and thus we will see a temperature rise. Now how much would the temperature rise if we add a given amount of heat? Now the amount of temperature rise depends on the mass of the system and also the system's ability to absorb heat affects the temperature rise. So this ability to absorb heat is characterized using specific heat. Specific heat is the amount of energy required to raise the temperature of a unit mass of a substance by 1 degree. So in this case, remember the mass is important and the temperature raise is important. Now, generally for water, specific heat of water is about 4.2 kilojoules per kilogram Kelvin. Now, when it comes to a gas, the process that we let the gas undergo during this heat addition is important. Depending on this process, the amount of energy needed to raise the temperature of 1 kilogram of gas by 1 degree Celsius changes. So we can have two types of processes in this case, constant volume and constant pressure. So the amount of heat needed to increase the temperature of a unit mass of substance by 1 degree at the constant volume process is called as specific heat at constant volume. And if the process is a constant pressure process, it is called as specific heat at constant pressure. Now please remember, this constant pressure or constant volume process is the process that we use to measure Cp, Cv values. However, you can use Cp value for a constant volume process. You can use Cv value for a constant pressure process. It might be not very clear at the moment. However, don't hurry to use Cp value if your problem says it's a constant pressure process. Or don't hurry to use Cv value if your process is a constant volume process. You have to consider more things than the process's constant volumeness or constant pressureness. Now, the change of temperature is directly related to internal energy. So let's talk about internal energy. So Joule did some experiments and demonstrated that internal energy U is a function of temperature only. That means U only changes with temperature, but pressure changes, volume changes does not affect internal energy. Since we know that PV equals RT is true for ideal gas and that the definition of enthalpy is equal to internal energy plus PV, we can show that H is equal to U plus RT. Now again, R is a constant and T is temperature, and we established U is a function of temperature only. So we can say that H is a function of temperature only for an ideal gas. Now we can say that du is equal to a constant into temperature. Now this constant is called as Cv, specific heat at constant volume. And when it comes to enthalpy, enthalpy is equal to Cp delta T. In this equation, the reason why we have Cvt dt is because we want to say that Cv is a function of temperature. Now when we want to calculate delta U or delta H, we can use the integration into Cv or Cp dt. Remember, delta U goes with Cv, delta H goes with Cp. Now in most of the thermodynamic problems, we have to calculate delta U and delta H values. Tabulated data is the most accurate way to calculate this. So for an example, for water, for refrigerant, you have tabulated UH data. So in that case, you can use them. If you don't have tables, what you can do is you can try to use CV or CP relationships. In these relationships, you have to use integration to calculate delta U and delta H. This gives a very accurate result. However, when you are doing manual calculations like in our exams, it's very difficult to use these relationships. So the other option is using average specific heats. Most of the time, this is what we are going to do. In this case, average stands for temperature average. As I told you earlier, CV, CP values depends on temperature. So when we are investigating a process that went from T1 to T2, let's say, uh, specific heats changes a little bit from T1 to T2. So you have to consider an average specific heat. When we are calculating average specific heat, we are assuming that the specific heat's change with temperature is linear. However, the change of specific heat from one temperature to the other is not going to be linear. Therefore, you will have a small error when you are using average specific heat. Now, earlier we established that H is equal to U plus RT, and we know that dH is equal to Cp dt and du equals to Cv dt. So we can conclude that Cp is equal to Cv plus R. So for an ideal gas, if you are given a specific heat, you can deduce the other specific heat if you know the R value for that ideal gas. Also, the ratio between specific heats is called as specific heat ratio, and we symbolize it using K. Most of these specific heat values can be viewed in your table A2. In table A2, there are several subtables, and in the first one, you have the values of Cp, Cv at 300 Kelvin. And in table A2, subtable B, you have CPCV values and R values for different temperatures. So the problem that you're talking is around 300 Kelvin. You can use table A2A. But if the temperature deviates considerably from 300 Kelvin, you have to use table A2B. Now that we have discussed about CPCV values for gases, let's consider incompressible substances. An incompressible substance is a substance where its volume doesn't change when you compress it or when you apply pressure onto it. So liquids and solids are considered as incompressible substances. When it comes to internal energy, there is no difference between gases and incompressible substances. You can show that internal energy change is equal to dV into delta T. So when you are calculating, you can calculate delta U using C average. So that is the uh, specific heat at T1 plus specific heat at T2 divided by 2 and multiply it by the difference of temperatures. However, when it comes to enthalpy change, things get a bit complicated. We know that enthalpy is equal to U plus PV, and we can use derivation to get this equation. dH is equal to du plus VdP PdV. This is a derivative of a multiplication. And since this is an incompressible substance, we know that dV is equal to 0. So this part cancels out. Now we can write for an incompressible substance, delta H is equal to delta U plus V delta P. Again, we can approximate delta U to Cv average delta T, and we have V delta P part. Now, when it comes to solids, delta P is equal to 0. So for a solid, delta H is equal to delta U, which is equal to C average delta T. But for a liquid, things are slightly different. If your liquid is going through a constant pressure process, delta P is equal to 0, and you will have the same equation delta H is equal to delta U. However, if your liquid is going on through a constant temperature process, delta T is equal to 0. So delta H is equal to V delta P. Because when delta T is equal to 0, delta U is equal to 0. Now this gives us this equation. Enthalpy at a given pressure and temperature is equal to enthalpy of the saturated liquid at given temperature plus specific volume of saturated liquid at given temperature into pressure change from saturated system. This gives you a much better approximation for a compressed liquid compared to the equation that we learned in chapter 3. So in chapter 3 we discussed that enthalpy or any property of a compressed liquid can be approximated to the property of saturated liquid at the given temperature.